Hi there. So this is part 2 of the calculus crash course for AP Physics. And part 2 is going to be on antiderivatives, definite integrals, and just integration in general. So in part 1, we talked about what a derivative is, right? It's a formula. Every function has a derivative. You can use that as a formula to calculate instantaneous rate of change. And the process of finding a derivative is referred to as differentiation. So now let's think about going in the reverse. So let's say that we're given a function and we want to think about finding the function whose derivative would be the given function. So where lowercase f of x is the derivative, what would be the function whose derivative would be lowercase f of x? And we're going to call that function capital F of x. Okay, so we're going in the reverse here of power rule for differentiation. So in order to get 2x squared as the derivative, that would mean that we would have to have 2/3 x cubed as the original term, right? Because we would then multiply 2/3 by 3 to get 2 and subtract 1 from the exponent. And then to get minus 3x as the derivative, that would have to be minus 3/2 x squared. You can double check that by thinking about taking the derivative of minus 3/2 x squared. And then to get 10 as the derivative, that would be 10x as the original term. So this could be capital F of x, whose derivative would be lowercase f of x, right? So we're saying that this would be equal to capital F prime of x. So next, let's think about writing a different function, g of x, whose derivative would also be lowercase f of x. Well, we know that the derivative of a constant would be 0. So couldn't we technically just add on a constant, pick some arbitrary constant to add on, and then the function g of x would have a derivative of lowercase f of x, like we could say plus 2. And the derivative of g of x would be equal to lowercase f of x, right? Capital G prime of x would also be equal to lowercase f of x. So by definition, both f of x and g of x are antiderivatives of lowercase f of x, meaning that f of x is their derivative. So capital F of x and capital G of x are antiderivatives. So a function capital F of x will be an antiderivative of lowercase f of x if capital F prime is equal to lowercase f. Also, if capital F of x is an antiderivative of lowercase f of x, then every other antiderivative of f of x will be of the form capital F of x plus c, where c is just a constant. So that's what I was getting at here. This didn't have to be plus 2. We could have chosen any constant, and then that still would have been an antiderivative of lowercase f of x. So all of the antiderivatives just differ by a constant. So this leads us to the indefinite integral of f of x. So the standard notation for antiderivative is using what we call the integral symbol, this kind of elongated S. So the integral of lowercase f of x, right? This was the rule for lowercase f of x. And notice we have this dx here, is an example of an indefinite integral. It represents the antiderivatives of lowercase f of x. So the indefinite integral indicates what we're doing to lowercase f of x, meaning that the quantity inside the parentheses is called the integrand. The symbol dx serves to indicate the independent variable, which might not always be x. And the process of finding the indefinite integral is indefinite integration, or just integration. Now, when you find the indefinite integral, you are finding the general antiderivative of the function. So in general, this is important, the indefinite integral of lowercase f of x is equal to capital F of x plus c. So you think about finding the antiderivative and you put a plus c to represent that arbitrary constant, the fact that all antiderivatives differ by a constant. So this was, that's right, I did that wrong. So my work was right, so what I have typed here is wrong. This should be 2/3 times x cubed. Oops. So 2/3 x cubed minus 3/2 x squared plus 10x plus c represents the general antiderivative. It represents the infinitely many antiderivatives of the function 2x squared minus 3x plus 10, which we called lowercase f of x. So what is the relationship between integration and differentiation? Well, since the integral of lowercase f of x represents the antiderivative of f of x, it follows that the derivative of the integral f of x dx is equal to lowercase f of x. In other words, integration and differentiation are inverse operations. Just like addition and subtraction, one undoes the other. So whenever you are differentiating, you're finding a derivative of a function. If you are integrating, you are finding the antiderivative of a function, which I always think about as like finding the original function. Just like with differentiation, we have some basic rules of integration. Unlike differentiation, where we had a rule to find the derivative of any given function, we are not able to integrate by hand every single function. You're going to continue to add different rules to your integration toolbox, but you will not be able to integrate necessarily any given function. But these rules will help us with integrating a number of them. So we had used power rule for integration, thinking about going in the opposite of power rule for differentiation. Constant rule, which goes back to kind of power rule to me. And then here are the integrals that follow, the antiderivatives that follow differentiation of the trig functions, right? So if we integrate sine, we get negative cosine because the derivative of cosine, remember, was negative sine. So in order for this to have a derivative, negative cosine to have a derivative of sine, in order for this derivative to be equal to positive sine, it has to be negative cosine. Okay, integral of cosine is sine, integral of secant squared is tangent of x. And it's very important when you are integrating an indefinite integral, you always have to put plus c. Super important. Always have to put plus c for an indefinite integral. Now, what else is super important is your notation. If you are integrating, you have to have the integral symbol as well as the differential dx, okay? And then whatever the integrand is, so whatever it is that you are integrating, if there are multiple terms, you need to have parentheses or some sort of a grouping symbol around the integrand. Just like with differentiation and just like with limits, you are allowed, if you have a function that you can think of as a sum or difference of functions, you are allowed to think about splitting the integral up and then adding up all of those integrals, so integrating each term. So that's why it's really important that you have parentheses around the integrand so that it doesn't look like you forgot an integral symbol or a dx symbol in your integral. And then there's also, since the derivative of e to the x was e to the x, the integral of e to the x is e to the x plus c. Since the derivative of natural log of x was 1 over x, the integral of 1 over x is equal to natural log of x, absolute value of x plus c. Now, this is a little bit tricky, right? The derivative of natural log of x is just 1 over x. If we think about the domain of natural log of x, that's for x greater than 0. However, if the function that you're given is 1 over x and you're asked to find the antiderivative, the domain of 1 over x is all real numbers except for x equals to 0. So by putting the absolute value bars here, this allows the domains to match up. So when you integrate 1 over x, you have to put natural log of absolute value of x plus c. And then substitution rule, I think will make more sense as we go through it, but substitution rule will allow you to integrate some more functions. So basically when you're trying to integrate something of this form, it's basically the opposite of chain rule. It's like the integration rule that goes with reverses chain rule. Okay, so let's go through some examples here. So let's integrate. I'm just going to say this is equal to. Let's integrate this function. Notice that the grouping symbols are there. We're integrating 6x squared minus x plus 6. So applying power rule for integration. The 6 you can think of as just hanging out there. And then when you're thinking about integrating x squared, that would be 1/3 x cubed. And then minus 1/2 x squared plus 6x. And then you have to remember plus c. So just cleaning that up a little bit, that's 2x cubed minus x squared over 2 plus 6x plus c. And you can do that in your head. You don't have to write that first step if you can do it in your head. Now, since the derivative of like 2x is 2, 3x, derivative of 3x is 3, right? Like you get the constant, whatever the coefficient is to the x. When you're going in the reverse and you are integrating a constant, you just have to add whatever variable it is that you are integrating with respect to. So if you're integrating with respect to t, you would get 3t plus c. But in this case, this will just be 3x plus c. Now, substitution rule. This is where it gets a little bit trickier. You don't know how to integrate this. Sometimes it's a little bit of trial and error, but the idea behind substitution rule is that you are rewriting the integral in a simpler form that you do know how to integrate. So you are rewriting it in terms of u. It's often called u substitution, u sub. So you are rewriting the integral in terms of u, and it will be in a way that you know how to integrate that simpler integral. So, you do not know how to integrate this as is. You could multiply, it is a polynomial. You could multiply out 2x minus 1 times 2x minus 1 times 2x minus 1, combine like terms, and then just use power rule for integration. That would be miserable. Or you can use u substitution. So what we're going to do for u substitution is we're going to have some side work. I'm going to label this. You don't normally have to, but it just so that you can see what our side work is. I'm going to let u equal to 2x minus 1. And I'm going to state that. Let u equal to 2x minus 1. So once we do that, then you think about what we have, and you don't normally have to write this step. I'll show you what you could go straight to. But now we have u cubed dx. Well, our integrand is in terms of u, but the differential is still dx. It's saying we're integrating with respect to x. So we basically need this entire integral to be in terms of u. So the way that we can do that is we look at u equals to 2x minus 1, and we think about taking the derivative of that with respect to x. Remember how I said one way to read dy over dx was the derivative of y with respect to x? Now we're going to find the derivative of u with respect to x, which, applying power rule for differentiation, would just be 2. And we want to replace dx. So we can think about solving for dx, and now we are able to replace this dx with du over 2. Which 1/2 can be pulled out front of the integral. And now this is something that we know how to integrate just using power rule for integration. The 1/2 can hang out there. You could have left the 1/2 in with the integrand as well. It's your preference. And what that would be 1/4 u to the 4th plus c. And then the last step is to substitute back in what you had let u equal to. So that'll be 1/8 and then 2x minus 1 to the 4th plus c. And you can always double check that you have integrated correctly. You don't have to write this in. I compare this to like back in Algebra 1 when you were first solving linear equations, like substituting your answers back in to make sure that you had the correct answer. So you could always check by differentiating the antiderivative that you got. And that would just require chain rule, right? So derivative of the outside, that would be 1/2 in front, and then to the 3rd power, leave the inside alone, times the derivative of the inside, and then the derivative of c would be 0. So this just ends up being 2x minus 1 cubed. And that means it worked, right? Because that is the integrand, those match. So this is the antiderivative that's fine, of the quantity 2x minus 1 cubed. So when we integrated, we found the general antiderivative. Okay, let's do another example of chain rule. Not chain rule. U-sub. Sorry, U-substitution. We're integrating. So the idea for U-substitution, and with practice, you get better at recognizing what you want to let U equal to, because that's the most challenging part. But whatever you let U equal to, you want the derivative of that to be left in the integrand so that it can cancel. So let's let U equal to the entire denominator here. So we would get du over dx, right? Differentiating u with respect to x would be 2x. Well, notice if we rearrange things here, we would get du over 2 equals to x dx. Because we need that x dx to be replaced. So we would have the integral of 1 over u du over 2. Because we had let u equal to x squared plus 4. And then to finish rewriting the integral, we replaced x dx with du over 2, which can also be written as 1 over 2 times the integral of 1 over u du. Well, the integral of 1 over u, that's one you were supposed to memorize. So we would have 1/2 times natural log of absolute value of u plus c. And then your last step is just to substitute what you had let u equal to back in. Now, x squared plus 4 is positive for all real numbers. So you actually don't need absolute value around x squared plus 4, around that argument. And that would be something that, like, if it came up as a multiple choice or something, you would have to recognize. Because those are both are the antiderivative. It's just the absolute value bars end up being unnecessary. Okay, let's try another one. So remember, what you let u equal to, you want its derivative to be left so that it can help you with replacing everything to be in terms of u. So if we let u equal to x squared, du over dx would be 2x. So we've let x squared be u, and then we still have x dx. So notice now from this equation, if we divide by 2 and we multiply by dx on both sides, we'd get du over 2 is equal to x dx again. So we'll have the integral of sine of u du over 2, which if you want to pull the 1/2 out right away, you can do that. And then when we integrate sine, that's going to be negative cosine. So this will be negative 1/2 cosine of u plus c. And then last step is to substitute that x squared back in for u. Okay, you could always pause and try this on your own and see if you're getting it, especially what you would want to let u equal to. Okay, I'm going to let u equal to what's underneath the radical. So then du over dx will be 3x squared. I need the x squared and the dx to turn into being in terms of u. So we could rewrite this as du over 3 equals to x squared dx. So then when we go to rewrite the integral, the 6 is still there, but the x squared dx gets replaced. And then we have 6 times the square root of u du over 3. So that 3 in the denominator there can divide the 6. So then that's 2 times the integral of u to the, I'm going to write as the 1/2 power du. And then just applying power rule for integration, that would be, or here, I'll write it this way, 2 times 1 over 1/2 plus 1 times u to the 1/2 plus 1 power. If you need to write this out, it's okay. Plus c. So what that would end up being 4/3 because it would be 2 times 2/3 u to the 3/2 plus c, and then substituting what I had let u equal to back in. Okay. So, this is a tricky looking one. If I let u equal to x squared, derivative of that would be 2x, and that wouldn't help me because then I'd still have the 1 over x in the exponent position there for e. So, why don't I try letting u equal to 1 over x, which is x to the negative first. So then du over dx, derivative of u with respect to x, would be negative x to the negative second, which is negative 1 over x squared. And then, oh, this is helpful, right? Because we want to replace that x squared that's in the denominator and the dx. So negative du would be 1 over x squared dx. So this will be the integral. I can pull that's like a negative 1, right? I can pull that out front of the integral. E to the u du. And then the integral of e to the u is just e to the u. So negative e to the u plus c equals negative e to the 1 over x plus c. Okay, so all of those were examples of finding the indefinite integral in order to find the general antiderivative of a given function. The given function being the one that was in the integrand position of the integral. So now let's look at the definite integral. The definite integral is whenever the integral is accompanied by what we call limits of integration. So this a and b would be referred to as the limits of integration. Unlike the indefinite integral, which ended up representing a function, the definite integral represents a number, a value. The definite integral represents, I put area in parentheses. I'll explain that more in just a second here. But it represents the area bounded by the curve of the function f and the x-axis on the interval from a to b. Now, when a function is just positive for all values on the interval from a to b, the definite integral would just represent this area. I'll write that out here. So the area, this area that I've highlighted in green, would be equal to the value of the definite integral here. So the area under the curve on the interval from a to b. So the area bounded by the curve and the x-axis on the interval from a to b. Now sometimes the function will either be completely negative on the interval from a to b, so below the x-axis, on the interval from A to B. Or it might be positive in some places and negative in some places. So if we look at this function, which on the interval from A to B is positive, let's say from like A to C, and then negative from C to B, the definite integral will actually end up giving us the difference between these areas. And what I mean by that is this would represent positive area. And then what I have shaded in orange, so from C to B, this would actually, I refer to it as like negative area. It would represent a negative value. Like the integral of f from A to C would represent this positive area. So from A to C, that highlighted in green would be positive area. This negative area, so this would be this value from C to B would be negative. And then the integral from A to B, in this case, would be taking that positive area and adding that negative area. So it would end up being the positive area, and then you'd actually end up like deducting the negative area from that positive area. Now there are some properties, which I've already kind of hinted at, for definite integrals here. There's the additive interval property, which this is thinking about the integral from A to C. So changing up the labeling of my picture, but I'll go back to my picture, which says that the integral from A to B plus the integral from B to C, and that's for B lying on the interval from A to C, would be equal to the integral from A to C. Based on my picture, I could actually say that the integral from A to B would be equal to the integral from A to C plus the integral from C to B. And that's demonstrating that property. So taking a value that lies on the interval and splitting up the integral to be a sum of those different intervals. The integrals based on those separate intervals. Now, the interchange of limits property says that the integral from A to B is equal to the negative integral from B to A. So the opposite. Remember, when we're talking about opposites in math, that refers to opposite sign. So it would be the opposite, and you switch the limits of integration. I call this the switchy property. The constant multiple property says that you're allowed to pull out if you have an integrand that you can think of as a function times a constant, you are allowed to pull out that constant if the limits of integration are the same number. So like you're integrating from 2 to 2. The integral is just 0. The area would be 0. The area under the curve would be 0. And then the sum or difference property says that if you have a function, just like with differentiation, and have, as we've seen with integration for indefinite integrals so far, but if you're integrating, you can think of as being a sum or difference of two functions, you are allowed to split up that integral. But how do we evaluate a definite integral by hand? We know that it represents area bounded by a curve in the x-axis. But how do we actually find what that value is? And to do that, we can use something we refer to as the fundamental theorem of calculus. Our textbook refers to this as the first fundamental theorem of calculus. There is a second fundamental theorem of calculus, and sometimes textbooks will reverse which one is the first and which one is the second. For us, this is the first fundamental theorem of calculus. And it says that if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of lowercase f, then this is what the definite integral will be equal to. So evaluating, there's one extra step we could write here, but if you were to integrate lowercase f of x using those same integration rules we just talked about, like power rule for integration, u substitution, you would find capital F of x if possible. And then those are your limits of integration. So the first fundamental theorem of calculus says that this definite integral is equal to capital F of b minus capital F of a. Okay, so let's go ahead and evaluate this definite integral. First step is to do what we were previously doing and integrate the integrand. So find the antiderivative. So that would be 1/3 x cubed minus 2/3 x squared plus x. Now, we would normally put plus c, but notice that if we put plus c here, and then you did capital F of b, you would end up with a plus c, and then you would be subtracting the plus c that goes with capital F of a plus c, and the c's would always end up canceling. So you don't, for definite integrals, you do not have to put a plus c. And our limits of integration are from 0 to 3. So then applying the first fundamental theorem of calculus, that will be 1/3 times 3 cubed minus 2/3 times 3 squared plus 3. So that's f of 3. And then minus, why did I put equals? Minus f of 0. So minus, I don't really have to write this out, but to demonstrate that fundamental theorem of calculus being applied. So this would actually just end up being equal to whatever that is. Whatever that value is. Which would represent the area bounded by the curve and the x-axis. So you could simplify that if you want to. Let me actually pull up Desmos here. Just to give you a visual. So if we were to type in the integrand, okay, the graph, and then just on the interval from 0 to 3. Okay. So this function is positive on that interval. It does, it looks like it has an x-intercept too. But basically, this value here, whatever that simplifies to, would represent the area bounded by the curve and the x-axis. So that first little section and then the second section. So it looks like from like 0 to 1 and then 1 to 3. You could even think about splitting up the integral for those two areas would be equal to whatever this value is equal to. And you can actually also have your calculator find that value. And if you want to come see me to find out how to do that on your calculator, if it comes up for you, I can help you with that. Okay. So we want to evaluate this definite integral. To integrate this, we have to do a u substitution. Remember, when you are doing a u substitution, you are rewriting the integral in terms of u. So when we do this, we're actually going to have to find new limits of integration for our integral that's in terms of u. We would want to let u equal to 2x. So du over dx would be 2. So replacing dx, that would be du over 2 is equal to dx. We would also need to figure out what we would want to replace -2 and 4 with. So our new lower limit of integration we could find by taking -2 and substituting it into what we let u equal to. So that would be 2 times -2 is -4. And our new upper limit of integration, we would do the same thing. We would take 4 and substitute into what we had let u equal to, and we'd get 8. So when we rewrite this new, this definite integral in terms of u, we're now going to be integrating from -4 to 8 e to the u du over 2. And by that constant multiple rule, we can pull the 1/2 out. So then when we integrate e to the u, we'll just get e to the u. We do not need to substitute what we let u equal to back in because we found our new limits of integration. The other approach you could technically use here is to think about integrating, doing the u substitution of an indefinite integral as side work and substituting what you had let u equal to back in, so everything's back in terms of x, and then use the original limits of integration, the -2 and the 4. But I don't want to do that step. I don't want to have to evaluate the indefinite integral first. I just from here want to apply the first fundamental theorem of calculus, which would give us e to the 8th minus e to the -4th. And we're done. Now you could pause this and try it on your own and then check your work. Again, need a u sub. So let's let u equal to 3x. So du over dx would be 3. So du over 3 is equal to dx, and we need our new limits of integration. So our new lower limit will be u equals to 3 times pi over 6, which would be pi over 2. And our new upper limit would be 3 times 2 pi over 3 So 2 pi. So rewriting our integral here, pi over 2 to 2 pi, sine of u, du over 3. I can pull the 1/3 out. And then integrating sine, the 1/3 will be there. I would get negative cosine of u. And then applying the first fundamental theorem of calculus. Okay, cosine of 2 pi would be 1. So that would end up being -1. Cosine of pi over 2 is 0. So -1/3. And that is the end of part 2 of our calculus crash course. So evaluating indefinite integrals to find general antiderivatives, and then evaluating definite integrals.